Hello, everyone. The timing of running code and rendering is all tightly defined and mostly deterministic. And that is thanks to the event loop. And if I do a half-decent job in the next 30 or so minutes, you'll know why things run in the order they do, and I don't know, it might even make sense, but there's no promises there. So, web pages have a thing that we tend to call the main thread. Here's the main thread. We call it the main thread because loads of stuff happens here. It's where JavaScript happens. It's where rendering happens. It's where the DOM lives. And this means that the bulk of your stuff on the web has a deterministic order. And we don't get multiple bits of code running at the same time, like trying to edit the same DOM and giving you a world of horrible race conditions. But it does mean that if something on the main thread takes a long time, and by a long time, I mean like 200 milliseconds. That's a long time in terms of user interaction. Then it becomes really noticeable because it's blocked loads of other things, like it blocks rendering, it blocks interaction. So although we have this main thread thing, we tend to spawn a whole series of threads, like for networking stuff, encoding and decoding, crypto, monitoring input devices. But once these threads have done something that the page needs to hear about, they need to sort of come back to the main thread to give it that information. And it's the event loop that orchestrates all of this. Like, take setTimeout, for instance. Is it badly named? Yes. Are the arguments in the wrong order? I'd say so. But have you thought about how it actually works? Well, let's write a web standard for it, because that's what I do these days. We'll start with the setTimeout method, when invoked, must run the following steps. Wait ms milliseconds, invoke callback. Done. But this isn't quite working. Because spec text, like this runs on the same thread as whatever invokes it. And in this case, it's invoked by JavaScript. So this is running on the main thread. So if we say, wait 5,000 milliseconds, we are waiting 5,000 milliseconds on the main thread. We're blocking lots of other stuff. So this spec is very sneezy right now, so we need to change that. And we do this. We run the steps in parallel, which is magic spec speak for get off the main thread, or get off this thread and run this stuff kind of at the same time as other stuff. But we've created a new problem here, because now we're invoking a callback from something other than the main thread. And I mean, there's no way this can really work. I mean, you would end up with lots of JavaScript running in parallel, still editing the same DOM, and you'd end up with all of these race conditions. So what we do is this. We queue a task, and we queue a task to get back onto the main thread at some point. And now we're calling JavaScript on the thread where JavaScript lives. So it all works. And this is a core part of how the browser works. Like, if you click the mouse, like, how does that get from the operating system into your JavaScript? It queues a task. When you fetch something, how do you get the response into your JavaScript? Well, it queues a task. And you send a message from a page to a worker, once again, it queues a task to do that. So the first part of the event loop I want to look at are task queues. And this is the oldest part of the event loop. Rather than look at the spec, I thought it might be easier to try and visualize the event loop. So here it is. This is it. I hope that clears up any questions you have. Actually, I really hope it does, because I based the whole talk around this one diagram, so I hope it works. But yeah, without anything to do, the event loop just spins round and round in a CPU-efficient manner. Now, this visualization is running at a fraction of a % of real time, and it's still kind of too fast to really see what's going on. So let's slow things down a bit. When we queue a task, the event loop takes a detour. So this detour here, this is where tasks happen. So at some point, the browser says to the event loop, hey, I've got a job for you to do. And the event loop is like, excellent, OK, add it to my to-do list, and I'll get round to it at some point. No problem, done. What if we do this? Like using setTimeout, we queue 2 callbacks that we want to run after 1 second, 1,000 milliseconds. Well, according to the spec we wrote, these 2 algorithms go parallel. Each waits for 1,000 milliseconds, and then they need to come back onto the main thread, and they do that by queuing a task. So the browser says to the event loop, hey, I've got something here that wants to do main thread work. In fact, I have 2 things, and it adds each one as a separate to-do item in the task queue. The event loop's like, sure, that's fine. I'll get round to it. So it runs the first callback. It goes around the event loop and runs the second callback. And that's tasks. And it would be pretty simple if that's all it was. but it gets more complicated when we think about the render steps. And this is what the browser uses to update what's actually on the screen. The render steps are another detour, and that involves style calculation. This is looking at all of the CSS that's going on and working out what applies to each element. Layout is creating a render tree, figuring out where everything is on the page, and where it's positioned. And then creating the actual pixel data, doing the actual painting. So at some point, the browser will say to the event loop, hey, we need to update what's on the screen. And the event loop's like, no problem, I'll get round to that next time I go around the event loop. Now, I don't know about you, but I would consider myself an expert at coding badly. I can take very simple bits of JavaScript and create infinite loops out of them in places I least expect. But let's take a closer look at what happens when I do that. Here's a page with a GIF and some text, and a big button that runs an infinite JavaScript loop. So if I click that button, everything stops. The GIF has stopped. I can no longer select text. The whole tab has kind of come to a standstill. Code for this is simple. This is just button click while true. So how do we actually visualize this? Well, the user clicks the button, so the browser says, hey, event loop, I've got a task for you. And event loop's like, yep, no problem, I'm on it. But this task never ends. It's running JavaScript forever. A couple of milliseconds later, the browser says, hey, event loop, we need to update that GIF that was on the page. So if you could just render at your next earliest convenience, that would be fantastic. And the event loop's like, yeah, OK, I'll get round to that right after I finish this infinite loop that I'm busy doing right now. Then the user tries to highlight text. And that involves hit testing. It involves looking at the DOM to see what the text actually is. So the browser says, hey, I've got a couple more items for your to-do list there. And the event loop's like, are you having a laugh? Do you know how long it takes to perform an infinite loop? It's a long time. There is a clue in the name. So that is why a while loop blocks rendering and other page interaction. But this is a good thing in practice. We look again at the code that I started with. I used to worry that this would result in a flash of content, but it can't, right? Because this script runs as part of a task, and that must run to completion before the browser can get back around to the render steps. The event loop guarantees your task will complete before rendering next happens. It still stresses me out, though. I'll always swap these lines around when I see it in code. So a while loop blocks rendering, but what about this? So this is a loop, but each time we go around the loop, we're using setTimeout to queue the next call. Well, let's find out. So very similar test to before. I click the button, and things are still working. In fact, it kind of looks like nothing's changed. But in the background, here's what's happening. We queue a task, go around the event loop, pick up that task, and we queue another task as a result. And that just keeps happening and happening until the end of time. But as we've already seen, only one task can be processed at a time. So when it's processed a task, it's having to go all the way around the event loop to pick up the next task. So and that means that at some point, the browser can say, we should update the display for that GIF. And it can. And it can go around and update the display. And that's why a setTimeout loop is not render blocking. But if you want to run code that has anything to do with rendering, a task is really the wrong place to do it, because a task is on the opposite side of the world to all of the rendering stuff as far as the event loop is concerned. What we want to do is we want to run code in the render steps. We want to run code here. And the browser lets us do that, and it lets us do that using requestAnimationFrame, another badly named function, I think, but it's really good for this purpose. RAF callbacks, they happen as part of the render steps. And to show why this is useful, I'm going to animate a box, just a box, and using this code. So I'm going to move that box forward 1 pixel, and then use requestAnimationFrame to create a loop around this. And that's it. That's all it does. So that's requestAnimationFrame. But what if we switch requestAnimationFrame for setTimeout? It looks like this. Now, this box is moving faster. It's moving about 3.5 times faster. And that means this callback is being called more often. And that is not a good thing. It's not a good thing at all. We saw earlier that the rendering can happen in between tasks. Yes, but just because it can happen doesn't mean it must. In reality, we can take a task. Should we render? No, can't be bothered yet. Go around the event loop, pick up another task. Should we render now? No, it doesn't feel like the right time. Many tasks can happen, and before the browser goes, yeah, actually, next time, we will update the display. And the browser gets to decide when to do this, and it tries to be as efficient as possible. The render steps only happen if there's something actually worth updating. If nothing's changed, it won't bother. Like, if the browser tab is in the background, if it isn't visible, it will never run the render steps because there's no point. But also, the majority of screens update at a set frequency. In most cases, that's 60 times a second. Some screens go faster, some screens go slower, but 60 hertz is the most common. So if we change page styles like 1,000 times a second, it's not going to run the render steps 1,000 times a second. It will synchronize itself with the display and only render up to a frequency the display is capable of, usually 60 times a second. Otherwise, it would be a waste of time. Like, there's no point rendering stuff the user will never see. But that's what setTimeout is doing here. It's moving faster because it's updating the position of that box more times than the user can see, more times than this display is capable of showing us. Also, so far, we've been using setTimeout as this kind of shorthand for queue a task. And it isn't really, because even though we've put 0 milliseconds for the callback, it's more like 4.7 is what the browser will use as a default. The spec says the browser can pick any number to use, but in the things I've tested, it seems to be about 4.7. There isn't a single method that just queues a task, but we can kind of fake it using message channels. And so I ran a test with that. And if you're sensitive to flashing images, it might be best to look away now, because that looks like this. There's so many tasks happening that it kind of just looks like the box is getting a random position. We're getting a task every 200th of a millisecond. So rendering can happen between tasks, but you can have many, even tens of thousands of tasks between renderings. OK, flashing images are gone now. Let's imagine each of these is a frame that is displayed to the user. So our rendering steps, they happen at the start of each frame. And that includes like style calculation, layout, and paint. Not necessarily all three every time. Depends what actually needs updating. But I like this. I like this. This is very neat and tidy. This is a beautiful picture. Tasks, on the other hand, they couldn't give a stuff. They just kind of appear anywhere they fancy. Like the event loop ensures that tasks appear they happen in the right order. They happen in the order they were queued. But in terms of timing within a frame, there is no kind of ordering here at all. And we saw this with our setTimeout. We were getting 4 per frame, 3 or 4 per frame. And that means that 3/4 of those callbacks were wasted effort in terms of rendering. Old animation libraries used to do something like this, where they were trying to use a millisecond value that's going to give them roughly 60 callbacks per second. And they're assuming a lot about the screen there. They're assuming the screen's 60 hertz, but that was the common case. So it kind of worked. It eliminated some of the duplicate effort. Unfortunately, it was a massive hack, because setTimeout is not designed for animation, and it really shows. Like, due to inaccuracies, you can end up with drift. So what's happened here is we're doing nothing in one frame, and then in the next frame, we're doing twice the amount of work. And that is a visual jank to the user. It doesn't look great. Also, if one of your tasks runs long, you can end up moving the render steps around, because it's all running on the same thread, and you're sort of disturbing their lovely routine that they have. If we use requestAnimationFrame, rather than setTimeout, it would look a lot more like this, kind of all neat and tidy, all nice and ordered. Everything is within the timing of the frame, even this longer task here. When I see like performance traces like this makes me happy. This is showing a good user experience. It makes me feel very calm. You can't avoid tasks completely, of course, because things like click events are going to be delivered to you in the task, and generally you want to respond to those as soon as possible, fair enough. But if you have things like timers, or you have stuff coming from the network, I really recommend using requestAnimationFrame to batch that work together, especially if you already have animations running, because you can save yourself a lot of duplicate work. There's one more detail I want to get to, and this is something that catches a lot of developers out. It caught me out. RequestAnimationFrame, it comes before processing CSS and before painting. So code like this might seem expensive, like we're showing and hiding a box many, many times. But this is actually really cheap. Like, JavaScript will always run to completion before rendering happens. So while you're doing this, the browser just sits back, and it lets you have your fun changing a value, and it doesn't really think about it in terms of CSS at all. And then at the end, when it actually comes around to the render steps, it goes, right, what did you actually change in the end? And the only bit that matters is this final line. And this explains a gotcha in CSS, or at least something that caught me out. I had a thing, right, that I wanted to animate from an exposition of 1,000 to 500. And that sounds easy, right? So I had my listener here. I set the exposition to 1,000. I told it to transition. And I changed the value to 500. But that animated from 0 to 500. And I was like, come on, browser, that isn't what I asked you to do. It's very clear. I said 1,000, transition to 500. What? I figured out that maybe I'm giving it too much information like, all at once. And it's the same reason we saw before. Like, the browser's not going to think about it, because I'm just in sort of one block of JavaScript. So it's going to ignore that first transform value. So, OK, fair enough. What I'll do then is I'm going to put this second bit, I'm going to put that inside a requestAnimationFrame. And now, it still animates from 0 to 500. And I was like, what is going on here? Well, I will tell you what's going on, because I finally figured it out. The user clicks on a button, and that's a task. So we come around to here. And this is where we set the initial transform and the transition. Fine. We queue an animation frame, and we go around. And this is where we set the destination, the final transform value. But the browser doesn't think about CSS until this next step over, the purple block there. This is where it calculates the CSS. So again, it totally misses the first value because it hasn't thought about styles in between those two things being set. And that's why, to make this work, you need to use not one, but two request animation frames. And now this will animate from 1,000 to 500. Incidentally, there is a hacky alternative to this. You can use something like getComputedStyle and just access one of the properties on it. And this forces the browser to perform a style calculation a lot earlier than it naturally would. But it makes the browser take note of all of the things you set up until that point. So it's like, oh, OK, transform, translate x 1,000. That's a thing that this element does. But you need to be careful with doing this, because you can end up forcing the browser to do a lot of extra style work than it really wants to. It only really wants to do that once per frame. In reality, the best way to deal with this would be the animation API, the web animation API, because you can just say, I want it to go from here to this other value, and it all just works. But that's only in Chrome, so it's not really worth talking about right now. So if the position of requestAnimationFrame within the render steps, if that was a surprise to you, if that was something you didn't know already, it's probably not your fault. You might have been misled by particular implementations, because Edge and Safari, they get this very wrong. They put RAF around about here. Most notably, they put it after paint. And that's kind of annoying, because it means that if the user clicks somewhere or something happens, and you want to batch that work using requestAnimationFrame, Edge and Safari, they will render before they get to your callback, so the user is going to see something. And that means that you're not going to see the actual changes you make until the next frame along. And that's adding quite a significant delay to things appearing on the screen. And it also makes it really difficult to batch work together. I hope this is something they fix soon. There's been activity on the bugs recently. But the web standards say it should be here, and that's where it is in Firefox and in Chrome. OK, that's enough about requestAnimationFrame. I want to take a look at microtasks. This is probably the least understood part of the event loop, I'd say. I strongly associate microtasks with promises. But this is not where they started. Back in the 1990s, browsers wanted to give developers a way to monitor DOM changes. And the W3C went, OK, we'll sort that out for you. And they gave us mutation events. So this is where I can say, OK, I want to know when a node is inserted into the body element. And fine, excellent. And you get a series of other events as well. But in practice, this was pretty problematic. Like, if we take this bit of code here, what I'm doing is I'm adding 100 spans into the body element. How many events would you expect to receive as a result of this? One event? One event for the whole operation? No. 100 events? One for each span? Yes. But also another 100 for this line here when the content is going into the actual span. A text node is going into the span. And because these events bubble, this simple piece of code is going to land you with 200 events. And because of this, like, relatively simple DOM modifications ended up triggering thousands of events. And if you were doing like a tiny bit of work in these listeners, that quickly became a big bit of work, and it was a performance disaster. What we really wanted was a way to sort of hear about a batch of this work. It's similar to what we saw with styles before. We want the browser to kind of sit back, let us do some stuff, and then at a convenient point say, some stuff changed. Here is a kind of an event or something to represent all of those changes. We want to hear about it once, not 200 times. And the answer became mutation observers, and they created a new queue called microtasks. A lot of documentation I read about microtasks suggests that it happens like, I don't know, every turn of the event loop, or it happens after a task, or something like that. And it is kind of true. There is a single place on the event loop where microtasks happen, but that is not where you'll generally encounter it. They also happen whenever JavaScript finishes executing. Yeah, that means that the JavaScript stack has gone from having stuff in it to having no stuff in it. And that's when we run microtasks. So you can end up with microtasks happening halfway through a task. You can have microtasks in the render steps as part of requestAnimationFrames, kind of anywhere JavaScript can run. So that means this JavaScript will run to completion, adding 100 spans and their contents. JavaScript finishes executing, and we get our mutation observer callback. Promises made use of them as well. So here, we queue a microtask, and then log yo. JavaScript is finished executing, so we go for the microtasks, and we log hey. And that means when a promise callback is executing, you are guaranteed that no other JavaScript is midway through at the time. The promise callback is right at the bottom of the stack, and that's why promises use microtasks. But what happens if we create a loop using microtasks? A bit like we did with setTimeout before. Same demo again. Click the button, and it blocks rendering. It blocks the tab in the same way a plain while loop did. Very different from setTimeout before. So promise callbacks are async, fine. But what does async actually mean? I mean, all it means is that they happen after synchronously executing code. So that's why we get yo before hey. But just being async doesn't mean it must yield to rendering. Doesn't mean it must yield to any particular part of the event loop. We've looked at 3 different queues so far. We looked at task queues, animation callback queues, which is where requestAnimationFrame callbacks happen, and now we're looking at microtasks. And just to make your lives a little bit easier, they all are processed very subtly differently. Like we've seen with task queues, we take one item and we take one item only, and if another item is queued, it just goes to the end of the queue, fine. Animation callbacks, they happen until completion, except ones that were queued while we were processing animation callbacks. They are deferred to the next frame. Microtasks, on the other hand, they are processed to completion, including any additionally queued items. So if you are adding items to the queue as quickly as you're processing them, you are processing microtasks forever. The event loop cannot continue until that queue has completely emptied, and that is why it blocks rendering. I run little JavaScript quizzes, and this is my favorite question. So I've got a button, and on click, I resolve the promise, and then log something. But I have 2 event listeners on the same element doing the same thing. So if the user clicks a button, what happens? In which order are things logged? Well, our first listener executes. Great, so that's on the JavaScript stack. Queues a microtask, and then we get to the next line where we log listener 1, and that is the first answer. Most folks agree on that bit, but what next? And I ran a Twitter poll on this last week. I've been speaking to a few of you saw it. Most people would say the next thing logged is listener 2, that's 63%. 5% of people think nan is just logged and then infinity. That is not the answer, but fair enough to that 5% of people. But yes, we got 63%. And listener 2 is the wrong answer. This is a real gotcha with script. But if you thought it was listener 2, then you're in very good company, so don't worry about it. Our listener has finished. So we've gone from having something on the JavaScript stack to nothing. So it is microtask time. We are going to run that promise, and we are going to log microtask 1. And there we go. And then it's time for the second listener, and that works the same. So the order is listener 1, microtask 1, listener 2, microtask 2. But that's if the user clicks the button. What if the button is clicked using JavaScript? Oh yes, it's different. For starters, our script is on the stack. We call click, and that synchronously dispatches the events. So we start with listener 1, great. We queue a microtask, and we log listener 1. And now it's microtask time. No, it is not microtask time. We can't run microtasks. This is where it's different, because our JavaScript stack is not empty. Button.click has not returned yet. So we move on to listener 2. We queue another microtask, and now we log listener 2. And this is where it diverges. And now our listener is done. In fact, all our listeners are done. Button.click returns, our JavaScript stack empties, and now we can process those microtasks, and they happen in order. And this has real-world implications. So beware if you're using promises in this way, or if you're using automated tests as well, because automated tests, if they're clicking things on the page, they're likely to be using JavaScript to do it, and that can change the behavior of your code. This also came up when we were looking at how to add observables to the DOM and how they'd integrate with promises. We hit this question. If we have a promise that represents the next click of a particular link, and it's just this little bit of code here, can someone use that promise and still call event.preventDefault? Promises are async, so have we missed our chance to prevent the default here? Turns out, no, it's fine. It's totally fine. This works. This just works. Unless, again, the user clicks the link, or some code clicks the link using JavaScript. And this is the final puzzle of the talk, because I'm overrunning a little bit. To figure this out, we actually need to take a look at the spec. So this is a very rough description of how the spec for clicking a link works. But we start by creating an event object, and then for every listener we have, we invoke that listener with the event object. And then we take a look at that. Has that event object's cancelled flag been set? If it's been set, then we're not going to follow the hyperlink. But if it's unset, we will follow the hyperlink. When you call event.preventDefault, it sets this cancelled flag on the event object. So if the user clicks a link, that's fine. Our microtasks happen here after each callback, because that's where the JavaScript stack empties. But when we call click with JavaScript, it's just going to call out to our process a link click algorithm, and it only returns once that algorithm is complete. So the JavaScript stack never empties during this algorithm. So our microtasks can't happen. So it hits this step 3 where it looks at the event object, and even if you've got loads of promises trying to call like prevent default, it's too late. It's going to follow that hyperlink, and then sometime later those promise callbacks happen, but you've missed the boat. You've missed the point where you can actually cancel that event. So remember that microtasks, they behave quite differently depending on the JavaScript stack. OK, so that 34 minutes, that was a massive brain dump of everything I know about the event loop and the various steps and various queues. I have found that knowing this stuff, it prevents that case where you've got a bit of code that's not doing what you want, so you just wrap it in a setTimeout, and now it kind of works sometimes. Knowing this stuff kind of helps avoid that. It helps me avoid jank by getting stuff running on the correct part of the event loop as well. And I hope I've managed to explain this stuff in a way that is helpful to you too. Like I said, I'm a stressful person, so as a result of this, I'm now going to go and collapse in a pile. But you've been a great audience. Thank you very much. Cheers.